Good evening, sir. I think I have to wait for another 5 minutes before I start.
No problem. Sorry.
So I think I'll start with the questions. Whoever joins, I will let them in. So for this week's question, I have taken some problems from week two, which is basically batch bioreactors, and you might have learnt about batch process entirely. So we will be solving some problems. Let's solve. I have around four problems, so we'll see how long it will take to solve them. So I'll move to the first question. So here is a question where determine the correctness or otherwise of the following. This is an assertion and reason based question. The first assertion is engineered Arabidopsis thaliana cells are cultured to high density for the production of polysaccharide gum. Oxygen limitation may occur in the system if there is an increase in cell concentration over time. So the reason given is in a system, oxygen limitation usually occurs when the rate of oxygen supply exceeds the rate of consumption. So what would be the answer? Out of the five answers given, what would be the answer? So if it would have been explained by ma'am, so the answer would be A is true, but R is false. Means the assertion, the first statement A is true, and the reason given for the first statement is false because usually the oxygen limitation happens when the rate of oxygen supply uh, exceeds the rate of oxygen consumption given. This is not the correct statement given. So that is why the answer would be A is true, but R is false. The next question would be there are three given graphs A, B, and C. Which of the following statement is or true based on the following figure? So we have been given product or biomass versus time graph where figure A represents only a non-growth associated metabolite production, B represents a mixed growth associated metabolite production, C represents non-growth associated metabolite production, and again C represents a growth associated metabolite production. Which would be the correct statement or statements given here? Any idea? There may be one or two multiple answers for this. So C is one among the answer. Indeed, C represents non-growth associated metabolic production because it looks like it is produced from the secondary metabolite production. So and B. So correct answer. So the figure B represents mixed growth where it is associated partially with our lag phase, which is growth and non-growth. So it is a primary and secondary metabolism involved product. So the next question is dioxic growth represents a phenomenon in which substrates are used in sequential manner by cultures undergoing multiple lag phases. Is the statement is true or false? Yeah, the answer is A, which is true. So the next question is a simpler mathematical problem where the question is a genetically engineered strain of bacteria is used to convert a substrate to a product in batch fermenter. In the exponential phase, the specific growth rate of this bacterial system is given as 0.45 R inverse. Which of the following substrate is R statements is R true for the system? So from I think you guys will remember the batch time regarding the statements given, like the lecture taken in the week 2. So here mu is given, which is 0.45 R inverse, and In case of this is a bacterial fermentation and it is a batch fermenter. So in case of this conditions, doubling time formula is ln of 2 divided by mu. So ln 2 is 0.6931, I guess, and substituting the mu values, it would be 0.45 R inverse. So the answer would be 1.5 something, so 1.54 R inverse. And they are talking about division rate in the um, options given below. So division rate would be, this is division rate, the rate at which the bacteria divides. So that would be 1 by doubling time, which is 1 by 1.54, means it is 0.65, okay, 65 R inverse. So the answer would be doubling time is 1.54 R inverse. So the answer is A, and your division rate is 0.65 R inverse. So the answer is A and C. A and C. Shall I move to the next slide? Yes. So this is also a simple, not it is like a derivation. We can derive it. So Zymomonas mobilis is used for conversion of glucose to ethanol in a batch fermenter under anaerobic conditions. For the system, let us assume the following conditions. There is endogenous metabolism cannot be neglected. So the KD cannot be neglected. So consider the cells to be in exponential phase where the specific growth rate can be approximated to maximum specific growth rate. So which of the following biomass accumulation rate equation is correct for the given batch system? So any idea where to start this derivation? Like how do we conclude which one of among the following is an answer, suitable answer? So then I will start. So this is also a batch system. So first step when you are writing any reactor based questions, it is first you should see whether it is a batch, fed batch, or continuous system. Depending on that, we can write our mass balance equation. So according to the law of conservation of mass, we can write input minus output. Yes, Karim? Hello? Okay. So input minus output plus your generation minus consumption is equal to accumulation. And we all know that in batch system, input is going to be there and output we will not be taking anything out. It will be taken out at the end of the fermentation. So input and output we can assume it is 0. So if we do biomass balance on both the sides, I hope you guys have gone through the week 2 lecture video so that these terms are not new for you. So when we do biomass balance on both sides, it would be dxv divided by dt equal to mu xv, as they have given that we cannot neglect our endogenous metabolism. We have to include that term also, where these the terms are mentioned here. whatever terms we are using here, it is mentioned on the side. So Kd is the rate of loss of cell mass due to cell death or endogenous metabolism. We have included that also. So if we assume that the volume is kept constant in case of batch reactor, as we are not going to add anything further, so our this equation will become dx by dt equal to, we will take the v out. Give me a minute. So dx by dt is equal to mu minus kd, the whole of v. If that is the case, we will be having dx divided by, this is x actually, this x will go down here and this dt will go down the upside. So dx by x equal to mu minus kd into dt. So if you integrate on both sides, it is integration of 1 by x is ln x by x naught, right? So if we keep the initial conditions and the final conditions and putting a limit, say dx by x to x naught equal to mu minus kd into, it is dt, given it is 0 to t, it will become ln of x by x naught equal to mu m minus kd into t. So if we, the closest option is here, we can do the reciprocal of this. That would be this one. Here it is. Answer A, which is ln of x naught by x equal to kd minus mu max, the whole power of t. So the answer for this would be ln of x naught by x equal to kd minus mu max into t. Uh, so we will go to the numericals. I want some of you to volunteer. There are only 4 people, so it's okay. So you so I will read out the question. This similar problem is solved in the multiple answers question also. So you guys can tell me what would be the first step or the formula. So during the exponential phase in batch culture, the growth rate of culture is proportional to the concentration of cells present. So when Streptococcus lactis bacteria are cultured in milk, the concentration of the cells doubles in 45 minutes. If this rate of growth is maintained for 12 hours, what is the final concentration of cells relative to the inoculum level? So anybody have any idea on what is given and what is expected to be solved. Okay, so I will start solving then. Maybe that will give an idea. So for the solution, so this is a batch study. So we will write an unsteady state mass balance equation for this. So for an unsteady state mass balance, your mass in minus mass out, and the rate of generation minus rate of consumption it would be. But in case of batch culture, wait a second, give me a minute. So we'll start solving. So for a batch culture, we all know that input is equal to output equal to 0. Input is equal to output, so we cannot input use that terms there. For the case of mass balance of cells, we will assume that there is no cell loss from the system. So rate of consumption is also 0. Then the rate of generation of the cells is proportional to the cells present, which is uh, we can write it as rate of generation is equal to generation of the cells, where your mu is a constant, X is cell concentration, and V is volume, culture volume. So now the total mass of cells, we will give a term as M, and it is equal to the culture volume. So if we include that into consideration, for a weight, if it is like when you multiply your volume into your mass, it will be equal into your cell concentration. So we can write that as d of V into X. X is your culture cell concentration, V is your volume. If you multiply it, you will get the value in terms of concentration, right? So by dt in terms of mass actually. For example, X is in the terms of grams per liter and V is in liter, means gram per liter into L is gram. So your Vx term will give you mass, which is M. So d into mass, differentiating mass in terms of with respect to time, nu x into V. So what how we can differentiate it. We can assume that as you know that volume is going to be constant throughout the batch reactor, because we are not going to add anything inside and we are not going to remove anything till the batch reactor is going to come to an end. So there is no change in the volume considered here. So volume is going to be kept constant. We can use differentiation here, U by V method, U by V for UV method, keeping V as a constant. We can we will keep U as a constant, so differentiating it, V dx by dt is equal to mu x V. This will give U VV on both sides. We can cancel it. Dx by dt is equal to mu x. So we will take x terms on one side, mu into dt. If we do integration of this, it is ln x equal to mu t plus k. Let us keep this equation aside, which is a constant. If at initial conditions, that is at the at the beginning of the exponential phase, growth phase, x is equal to x naught, then at t is equal to 0, which is at the initial state. So ln of considering this here, ln of x naught is equal to mu into 0 plus k. We will be getting ln of x naught equal to k. So substituting, let us keep this as equation 1, this as equation 2. So substituting equation 2 in 1, which is ln of x equal to mu t plus ln of x naught. We can take this here, which is ln x minus x naught equal to mu t, which can be otherwise written as ln x by x naught equal to mu t. This is how you would have solved this, but for those who want to solve to just brush up things, I'm doing it again. So now we have come to the equation where it is relating your time and your inoculum. So let's go back to the question what they have asked. So they have asked if when the streptococcus bacteria are cultured in milk, the concentration of the cells double in 45 minutes. If this rate of growth is maintained for 12 hours, what is the final concentration of cells relative to the inoculum level? So in this case, in case if your cell is doubling, if your initial inoculum level is x naught, in case of doubling, what will happen? It will increase twice, 2 times. So x naught will be 2 equal to 2x naught in case doubling happens. So just given that doubling happens every 45 minutes. So we will try to at x naught, x initial level it was x naught. During the exponential phase, when your doubling is happening, it is 2x naught because it is doubled. So let us consider that as the final concentration during doubling. And later instead of x, we will put 2x naught. X naught here. Your mu we don't know. And 45 minutes. So it is ln 2 equal to 45 mu. Ln 2 is 0.6931 divided by 45 is equal to mu. So the mu, what would be the mu value? The mu value is what actually? 0.0154. So the unit we should make sure we are including the units everywhere, otherwise we cannot detect. So the unit will be minute inverse, which gives you the specific growth rate. So still we just found out the mu value. So therefore if we substitute this in our equation, let's keep this as equation 3. If we substitute this in equation 3, ln of x by x naught is equal to 0.0154 into t. We will take ln on both sides. If we take ln on both sides, it would become x by x naught equal to e power of 0.0154 into t. Means x is equal to x naught e power of 0.0154 t, where t is your time. They have given what they have given. If the rate of growth, we have found the rate of growth. If the rate of growth is maintained for 12 hours, what is the final concentration of cells relative to the inoculum level? What would be the final concentration of cells at the end of 12 hours? So in terms of minutes only we are calculating. So we will convert 12 hours into minutes. So 12 hours into 60 minutes is 720 minutes, right? So x is equal to x naught e power of 0.0154 into 720. So if we do that, it would be around what? X is equal to x naught into 10 to the power of 4. There it will be much, it is coming from 6.5. So your after 12 hours, the cell concentration would be 6.55 into 10 to the power 4 times the cell concentration at the beginning of the exponential growth. So when you are asked question like this, you have to mention that the cell concentration, you have calculated for 12 hours, right? Cell concentration at the uh, or after 12 hours would be 6.54 into 10 to the power of 4 times the cell concentration of. This is what this equation implies. Your final concentration would be 6.5 times into 10 to the power 4 times the concentration of the initial cell concentration, which is at the beginning of the exponential growth. So um, you guys remember the growth phases of the bacterial cells, right? Not only bacterial cells, all the cells, how it grows. Anybody, can anybody tell me? Yeah, so it is a sigmoidal growth curve, where here would be the lag. This is log or exponential. This is the stationary, and here is the
Death phase.
death phase. So in case of your lag phase, the cell concentration would be the same as the inoculum level. So how much ever if you are solving any problems, your cell concentration is dealing with the lag phase only they are asking about, means it will be closer to your initial inoculum level. So keep that in mind. In case of exponential phase only, the growth continues to start. So let's go to the next problem. I think this one is a pretty easy one, but still, I do anybody have graph sheets? If it is not there, it's okay. I will tell you guys how to solve it. You can do it when you have free time. I don't think anybody will have. It's okay. So let me read out the question. A mouse hybridoma cell line is used to produce monoclonal antibodies. So growth in the batch culture is monitored with the following results and determine the specific growth rate during the growth phase. We have to calculate the mu value during the growth phase. So if we calculate, how do you calculate the mu value? If your time in days is given and cell concentration is given, cells per ml is given. So when the both is given, you were given any values on related to growth. You know the specific growth rate ka form unit is in time inverse, right? So what could we do here? What we can keep it as x-axis and what as a y-axis? Any idea?
Time in the x-axis, ma'am, and cell concentration in the y.
Yes, sir. So we can keep cell concentration in the y-axis and your time in the x-axis. We can draw if you plot the values given, this will have only if we have a graph we can see that. So if we plot, say for example, if the graph is somewhat like this, there would be a slope. We can take a slope of which we can get mu. So from the slope you can get mu value. If you get the mu value, we can easily calculate doubling time also. So the formula for doubling time is what it is. Doubling time is ln of 2 divided by your mu. So if a graph is given like this, you can plot the values, plot the graph, get the slope value which will give you the mu value which is the specific growth rate, and from your specific growth rate you can calculate the doubling time. So anything which is related to this can be easily calculated if these values, any graph sums are also given. So that is a simple one. When you have time, when you have graph, you can try doing it. Even in the Excel you can do that. So let's go to the proper batch culture problem where uh, we'll take a break for 2 minutes and then we will start. So have everybody submitted your assignment questions week 1 and 2? Yes. So in somebody has raised the question like in discussion forum that it is going to rocket propulsion um, something. So it is actually if we yes, then it become normal, right? Is the issue being resolved?
I think it's resolved right
Yes,
now.
yes, yes. Thank you, sir.
Ma'am, one question.
Yes,
Is the
sir.
exam going to be as tough as this?
I I cannot answer that one, sir.
Just
Yes, like if we understand the concepts, I think it will be easier only. Like
okay.
the problems I am taking, the like it won't be that simple. That I can assure.
Okay.
Yeah, it is just some. I have a mixed audience, so I have to cover them. So that is why I'm.
Sure, sure,
Yeah,
sure, sure.
but we cannot expect the same in the exams.
Okay. Thank you.
Yes, sir. I think we can start solving. So one more question we have apart from this question, then we can move on. So this question will look similar to the next question also. So you can solve the next one. So let me read out the question. So Zymomonas mobilis is used to convert glucose to ethanol in a batch fermenter under anaerobic conditions. The yield of biomass from substrate is 0.06 gram per gram and your product yield is 7.7 gram per gram. The maintenance coefficient MS is 2.2 gram per gram. The specific rate of product formation due to the maintenance is 1.1 R inverse. The maximum specific growth rate of Zymomonas mobilis is approximately 0.3 R and 1.5 gram of bacteria are inoculated into 50 liter of medium containing 12 grams per liter of glucose. Determine the batch culture time. Note this, it is batch culture time, which is TB, to produce 10 gram of biomass. This is question A. And to achieve 90% substrate conversion, what would be the batch time? And to produce 100 grams of ethanol, what would be the batch time? So the entire problem is about batch time. I hope you have come across, like I saw like in week 2 you were the question, like the theory covered was about the batch cultures and batch reactor. So I think everybody remembers some of the problems. So I want you guys to follow the steps what I am doing. So let's first start with writing down the given values. So given would be your yield with respect to biomass and substrate, which is YXS is given, which is 0.06 grams per gram, and your yield with respect to product is YPX, which is given as we can write YPX also or YP slash X also, and YPS is 7.7 grams per gram, and your mu max is given. Mu max is 0.3 R inverse, and what else is given? Maintenance coefficient MS is 2.2 gram per gram hour inverse, and MP, maintenance with respect to product, is 1.1 hour inverse. So what we can calculate from here, it's also given that volume is 50 liters and that 50 liter volume contains 12 grams per liter of your glucose, and the inoculum is actually it is our 5 gram. This is not, this is our inverse actually. So this is 5 grams. So our inoculum is 5 grams. So as a mass value it is given, as we know that 5 gram inoculum, 5 gram of inoculum in 50 liter is our X naught, means the concentration of the cells, concentration of bacteria. Yes, we can find it from here, which is 0.1 grams per liter. So we can find X naught equal to 0.1 grams per liter, and it is given that your solution contains glucose 12 grams per liter. So S naught, your substrate is glucose, right? Glucose is going to convert it to ethanol here by the bacteria. So S naught is 12 grams per liter. So these are the things which are given there. So let's come to our first question. Determine the batch culture time required to produce 10 gram of biomass. So for a biomass of if 10 gram of biomass are produced by the reaction, then the final biomass would be what? Initially we have added 5 grams initially, which is X naught. Like, yeah, initially we have added X as 5 grams, and now you want the extra additional 10 grams of biomass. So it would be total at the end of the reaction, it would be 15 grams of biomass. So at the final, which is XF, the biomass concentration would be, the volume is going to remain the same because it is a batch reaction. So in the batch reactor, we are not taking in the middle, nothing we are taking out. So nor we are adding anything. So it is the same. So 15 grams per 50 liter. If we do that, it is 3 by 10, so 0.3 grams per liter. So batch time, there are various versions of this same formula. When we were deriving, you could have noticed. If you have any doubts, you can refer Paul Doran by the bioprocess principles by Paul Doran. I have given the, I hope you have received the link for the drive where the books are being kept. So for batch time, the formula would be 1 by mu max ln of xf divided by x naught. So substituting this x naught, we have 0.3 grams per liter. X naught is 0.1 grams per liter. We have found previously. Here you can see here we have seen x naught is 0.1 grams per liter. Let's just solve it. So mu max is also given. It is 0.3 R inverse. So 1 by mu max ln of x of s 0.3, x naught is 0.1. If we solve this, how much it is coming? Around this ln 3. Which is 3.30 into 1.0986. It is around 3.65. approximately we can write 3.7. So yes, sir, it is around 3.65 to 3 point. So it is your batch time. We have solved A. This is A. With, sorry. So it is to produce. We have determined the time required batch time required to produce 10 gram of biomass from the given values. Now the next question would be determine the batch culture time required to achieve 90% substrate conversion. If we need 90% substrate conversion means 90% in the sense 100 minus 90 is 10%, right? So 10% means 0.1%. So 90% conversion means substrate has been 90% already converted. So only the final substrate concentration would be only 10%, which is 0.1 gram per liter. 0.1 means 10% of what we have added, which is what we have added around initial glucose concentration is 12 grams per liter, right? Yes, not. This is 0.1, just 10%, or we can write 10% of S naught. What I was telling is initially we have added a substrate of 12 grams per liter. 90% of that 12 gram per liter has been already converted, means the remaining would be what? 100 minus 90, just 10%. 10% of S naught, just 0.1 into S naught is 12 grams per liter. It is given 12, means 1.2 grams per liter. So SF with 1.2 grams per liter. So in terms of substrate, we can write the formulas for substrate conversion, where you would have seen while deriving the batch equation, design equation, we would have seen this. In that case, the formula is, please note the formula, batch time 1 by mu max ln of 1 plus S naught minus XF 1 by YXF plus MS plus mu max into X naught. If we substitute all the values, we know all the values for whatever is given here. If we substitute this, we will get answer for the time required to produce 90% conversion of your substrate. So if we start solving it, it would be 1.1 divided by 0.3 ln of 1 plus S naught is 12. So 12 minus SF is 1.2 divided by 1 by y-axis is what? Y-axis is 0.06. MS is 2.2. 0.06 plus 2.2 divided by mu max is 0.3 into 0.1. We solve this. Plus 10.8 2.2 divided by 0.3 is 1.33 into 0.1. Minus 1 plus 0.8 divided by 0.7 plus 4.5. Should be 5.68 something. We can approximately tell that 5.7 hours. So the answer for the batch culture time required to produce or achieve 90% substrate conversion is 5.7 hour. The unit is important. So come to C. So calculate the time required to produce 100 gram of ethanol. Ethanol is our product. So the first thing which we solved is with respect to biomass. The batch time we have calculated with respect to biomass. The second one is with respect to substrate we have calculated, and with respect to product also there is we have left to solve. So let's start solving that. So I will write the first I will write the equation, then we will see what and all we need to find. In case of product, this is Harita, can you please mute your call? Thank you. So to calculate the batch time with respect to product, we can use this formula 1 plus mu is 1 plus mu max P product final product concentration initial product concentration divided by x naught initial cell concentration into QP, where QP we can calculate using this term QP. Yield with respect to product multiplied by your maximum specific growth rate plus your MP. Your MP is already given. This is also given. This is also given. So we can calculate QP. So QP is equal to 7.7 into 0.3 plus 1.1 is equal to 3.4 RMS. So as QP is also given, we have found QP also, and we know that P naught value is 0. How? Because Initially, when you are performing any reaction, or you are keep putting everything together inside a reactor, there is no product going to be there unless it is an autocatalytic reaction, where in case of autocatalytic reaction, your inoculum is the final uh, the thing the substrate of something which is going to catalyze its own production is called autocatalytic reaction. But here it is not an autocatalytic reaction. Your product is ethanol. In the initial start of the reaction, ethanol is not going to be present. So here we can assume that P naught is equal to 0. So when P naught is equal to 0, you need 100 gram of ethanol, means you need PF. So at PF is the concentration of your product at the final, which is at the end of the reaction when it ends inside the reactor. What would be the concentration of the product? So here the question is, to produce 100 gram of ethanol, the mass is already given. You know the volume, so it would be what? PF is equal to 100 gram of ethanol is you want, and you have 50-liter volume. So it is 2 grams per liter. So your PF is 2 grams per liter. Now you have PF. PF is there. P naught you know 0. You have QP. And what else you need? X naught you know. Mu M you know. Just substitute the values. Let's start substituting it. So from so please substitute and tell the answer. It is TB equal to 1 divided by 0.3 ln of divided by 0.1 into what is QP value? It is 3.4, 3.4, 2 grams per liter. So now please substitute and answer. Recipe point 0.34. This will be around 3.36. Our inverse approximately 3.4. Our actually not our inverse. So if you have any clarification in this problem, you can ask. Based on this only, we will do the next problem. I'll give 5 minutes time for you to solve. If you're done solving, please let me know.
Done, ma'am. Thank you.
Thank you, sir. Then I'll go to the next problem now. So our next problem is glucose is being used for the production of E. coli in a 1200 meter cube bioreactor. 60 grams per liter of glucose is being fed into the system with a substrate conversion of 95% in the process. The biomass yield from the substrate is 0.55 gram per gram. Assume that the specific growth rate is approximately equal to mu max, which is given as 0.5 R inverse. For this batch mode of operation, the initial cell concentration is 0.1 gram per liter and the downtime between the batches is 20 hours. So calculate the batch time in terms of hour. The second question is total mass of cells produced per batch in terms of kg, and total number of batches in a year. Total mass of cells produced annually during the batch culture in terms of tons per year. And the fifth question is, if the desired annual biomass production is to be 15,000 tons per year, what should be the volume of the reactor in meter cubes? So I think this one resembles your assignment problem. So you would have solved, I guess, but still I would solve for the others who would see the videos in the future. So let's start. Let's start writing down what is the given, what are the details given for us. So the solutions which is given is volume is 1200 meter cube. We will convert it into liters. 1200 into 10 to the power liters, where 1 meter cube is equal to 10 to the power cube liter. Okay, 60 gram of your gram per liter of glucose is being fed into the system, which is your S naught. So we know S naught is 60 grams per liter, and the conversion is 95% in the process. 95% conversion is there. And the biomass yield from the substrate, which is YXS, is 0.55 grams per gram. And we are asked to assume the specific growth rate is approximately equal to mu max, which is given as 0.5 R inverse, which is mu is equal to mu max equal to 0.5 R inverse. For this batch mode of operation, the initial cell concentration, which is X naught, is equal to 0.1 grams per liter. And downtime we will note is 20 hours. So these are the ones which are given. So with these values, we will see what we can calculate, and from here we can calculate the value of final substrate concentration. How we are given it is 95% conversion, so 5% of substrate is going to be remaining. So 5% of S naught, which is 5% is 0.005. 0.05 into 60 grams per liter, which is around 3 grams per liter, SF, which is equal to SF. So we have found all the necessary things needed. We will choose, what is the first question? Calculate the batch time, just the batch time. So as we have our substrate values here, we can easily incorporate that into that and calculate, where the batch time is 1 by mu max ln of 1 plus y x naught okay. So for this, mu max is 0.5 ln of 1 plus y x value is, the yield with respect to substrate is 0.55. So our x naught is 0.1. Substrate initial is 60. Later on it became 3. So if we calculate, it's ln of 3, 5.75. This is 11.75, I guess. 11.5 hours. So the batch time is TB is 11 point. For answer for 1 we have calculated. Thank you sir for answering. So now we will do the next part, which is total mass of cells produced per batch. Here mass is asked, not the concentration. So start calculating that. In our previous problem we saw how to calculate mass. So the final total mass it's necessary. So x naught e power of mu max into TB. This we have calculated from our I think you remember that our ln of x by x naught equal to mu max by t, that formula. From here we have come here, It is a derived form of this. So we can we know our x naught value, which is 0.1. E power of mu max is 0.5 into batch time is 11.5. Yes. So we calculate xf is 31 something 0.4 grams per liter. So now we found the concentration of our final concentration of biomass, but what asked was the total mass, just not the concentration. And we know the volume we have calculated. What we have calculated, the volume is in terms of meter cube. It is we have calculated in terms of liters. So 12,000 into 10 to the power 3 liters. So the volume is 10,000, 12,000 or 12 into 10 to the power 5 also we can write. Liter. So weight by volume will give our concentration, right? So we need total mass of the cells. We can calculate from here, which is what was the final and what was the initial. Final minus initial divided by V will be total mass produced, which is being newly produced. We'll keep that as X. So please understand the terms will be confusing. We have to understand what exactly they are asking for. So when it is asked as total mass of cells produced per batch means we are initial inoculum should be neglected because it is given by us. Whatever is being produced only should be considered. So that is why we want to minus the final minus initial. So if it is the case 31.5 31.4 grams minus our inoculum, if we minus it, divided by your volume, which is 12,000, 1200, 1200 10 to the power cube, which is, we calculate, it is coming around 3000. 31.3 divided by
Ma'am, should we not multiply by the volume?
yes sir, I got confused. Yes sir, there is a confusion. I confused it actually. We have to multiply it by volume into V. So if we do that, it will come around 3,754 to 10 to the power 3 grams. But we wanted in kgs, So if that is the case, it is 3,7584 kgs. So this would be our total mass produced. So we'll go to the next one, which is C. Sorry. So the total number of batches in a year. So our batch time we have already calculated, which is our batch time is 11.5 hours, and the downtime is given as 20 hours. So total time would be 31.5 hours, which is TB plus TD. So now per year, if we calculate how many batches means, for a year it is 365 days into 365 days into 24 hours, converting them to hours. And 76 hours. This divided by our 31.5. So 8760 hours divided by our 31.5 hours will give us 278.09 runs. So per year we will be getting around 278 runs approximately. And for the question D, total mass of cells produced annually during the batch culture. We should mention in terms of tons per year. So in case of annual production, total biomass we have total biomass produced into number of tons. This will give us annually how much biomass can be produced. So our total biomass would be 37584, right? 37584 kgs. This into 278 tons. So 1 ton is 10 power of 3 kilograms. So what this would be 237 into kgs, which is 1044.352 tons per year. This is our annual production. So now our last question is, if the desired annual biomass production is to be 15,000 tons per year, what should be the volume of the reactor in meter cubes? So if I fix our annual production is 15,000 tons per year, then we should back calculate the volume of the reactor. So for that we will do the same formula as here we can use. So for annual production, excess of biomass into number of batches, that is runs. So this we know 15,000 tons per year. How much we X required we don't know. Into number of batches we know 278 runs per year, we can run only 278 runs. So with this we can calculate the amount of biomass which we need which needs to be produced to make an annual production of 15,000 tons per year. So that would be 15,000 divided by 278. It should come around 53.95, around approximately 54 tons. So our X value would be 54 tons. If it is 54 tons of biomass has to be produced. So to produce a biomass of 54 tons, then how much volume is required? The same formula as before. X required is equal to xf minus x naught into volume. We know x required, which is 54. We will take 54 our xf value is 31.4 and 1.1. 31.4 minus 0.3. So here the volume is in what is around grams per liter. Fifty-four divided by, yes sir, it is 172, yeah, 1720 something. So I think that would be the end of the I have that would be the end of the session. I don't have any more questions.
Thank you, ma'am.
Yes sir, thank you sir.
Ma'am, there's one question
Yes,
in week two.
uh
Uh,
which one sir?
the week two,
Week 2.
yeah,
Okay.
if you don't mind, the Luong's equation,
Okay.
uh, I think they have mentioned it wrong.
I think that in the discussion forum, that question has been asked, right, sir?
Yeah, I've
Yeah.
asked it.
Yes. So I think the answer has been, I think the respective person is working on that
Okay.
and they have found it. I think the answer has been posted. I don't know why it is not reflecting that. I don't know. I will check with them.
Okay. And the link which you said for the books,
Yes, sir.
that
Is it not
does
shared
not.
with you?
No, it's not been shared, ma'am.
Not been shared. Okay, I'll check, sir. If not, I will in next class by the next class.
Yeah.
It is actually available online. I will check 1 minute, sir. Let me put the book's name or link. If I get, I will put it up down there. Wait a minute. I will check.
Yeah.
So you can download the book from this link. If I have already given them the link for some books which I have already added, but I don't know why it is not reflecting there. But you can use this link to download this particular book which I'm using to solve the tutorials.
Thank you, ma'am. Thank
Yes,
you.
sir. Thank you.
And thank you for your time. Thank you very
It's okay.
much.
Thank you, sir. So let us solve this question number 7, which we have left before. Now let's solve the question number 7, which is mouse hybridomous cell line cells used to produce monoclonal antibody. Growth in batch culture is monitored with the following results. I determine the specific growth rate during the growth phase, and I hope like so here I have given, as we don't have any graphs to solve, let's see how this can be solved. So here the time period is given in terms of days and cell concentration in terms of cell ml per liter, milliliter into 10 to the power minus 6. By just let's see how we can plot this. We'll try to solve. We can use semi-log graph here, but let's see. Okay, let me take it to the next slide. Okay. Okay, so let's see. Time we will write 0.2, 0.5. Okay, that's 0.5, 1, 2, 0.51, 1.52. to the next slide. Give me a minute. Here 0.45 divided this 2 at the maximum it is 4, right? So we'll write same legends. Okay, it is 0.45. So let's try to put those values in the graph. So for 0, we will put, I'm just keeping this as an example. So please try to solve it in a graph sheet. For 0.2 it is 0.2 it is 0.52, and 0.5 it is 0.65, point 0.1 it is 0.81, here 1.5 it is 2, and divided 1.77, 2.5 is 2.1, so it is rising actually. 3 point, for 3 it is 3.55, it is increasing a lot. 3.5 it is 4, the maximum. 4 it is coming down, and 4.5 it is 2. So it is like an S, right? Okay. So in this we have to determine the mu max value. It looks like an S-shaped curve, so we can take an slope. We take slope. Slope is equal to mu. So take the slope, for example, here. Say for example, this is not the answer. 0.6. So if your slope is equal to 0.6, then it is equal to mu. So from this mu we can calculate doubling time. So what is doubling time? Which is ln of 2 divided by 0.6. The unit is important, which is the inverse here. Ln 2 is 0.693 divided by 0.6, which would be approximately 3,000, approximately 1, which is 1 day. So doubling time is 1 day. So that's all. This is how you have to solve. So in the next class, if somebody can get graph sheet, that would be fine. So I hope you guys have received the link for the books which has been shared. If it is not received, please write to us. Please mention in the discussion forum. The question is regarding the live session held on Friday 6 to 8. So please try to join at 6 o'clock. I think there are nobody else left in the meeting. Yes. To try to solve some other problems. Now we will solve the derivation which was a little bit tricky, which was for question number 5 for according to the law of let us write in terms of accumulation equal to input output plus generation for a batch system. Let's do biomass balance. D of x into v divided by t is equal to mu xv minus kd xv. Kd is included. as mentioned in the question. Hmm. So now if we assume C is constant, then dx by dt is equal to mu minus dt on derivation mu minus kd into dt. Zero to t, which is the limit, x to x naught to x minus plus 1 by x So this is how, if we multiply this option to get the closest option, actually the first option is not given here. So if you multiply the entire equation by minus, it will change into minus ln x plus ln x naught equal to minus mu plus kd into t, which can be rewritten as ln x naught minus ln x equal to kd minus mu into t, further which can be modified into ln of x naught by x into kd minus mu into t. This is how the answer for question 5, which is option A, I guess, was arrived. So that's all for the session. Thank you for joining the session. We'll meet in the next class.